In previous videos, we have looked at what happens to a coil of current carrying wire when it's encased in or embedded, I should say, in a magnetic field. So I've drawn here a magnetic field, and then I've given you a loop of current, and I've drawn in, if I use the right hand rule to wrap my fingers around the current, this will tell me the magnetic moment of this mu looks like this. So there's an angle between mu and the B field that is not zero. So what does that mean? Well, from how we've talked about this already, we know that it's going to experience a torque, and that torque will act such that the magnetic field and the mu vector attempt to align. B rotates, if it's free to rotate, will rotate this thing around until mu aligns it. Now we've also seen that the inertia of this thing will cause it to rotate past that point, and if it's not mechanically altered in some way, this thing is just going to oscillate. We've seen that. But what I want to look at it from now is not a torque perspective, but an energy perspective. So let me just remind you of how potential energy works. If I leave this pin here, is it going to do anything? And the answer is, well, no. Tell me why in terms of energy. And we would say that's because the potential energy of this pin is minimized. Now, we've got to be careful saying things like, well, it's zero, or it's, 10 joules or whatever. Because with potential energy, remember, the only thing that's physically meaningful about potential energy is how it changes from point to point. So I can say that this is potential energy 0. I can say it's potential energy 1 billion joules. It doesn't actually matter. What matters is how it changes if the pin moves. But the pin's not moving, right? And it's not likely to move because there's a desk here. So what we can say about the potential energy of the pin is that it's minimized. Okay, look at this system. Is the potential energy minimized here? Well, I would say definitely not. Well, how do I know? Well, if I let this thing go, it's going to move. It's going to rotate and attempt to line itself up. So I think what we have to say here is that the potential energy is not minimized here. But if I draw another loop, and I will draw it, wrap my fingers around the current. So the current's coming up behind the page and down in front of the page, and I get a magnetic moment in that case that looks like this. Well, now, if this current is just sitting here and I flip on the field, right? There's no field, this is the current, and then I turn on the field. Is this going to do anything? And the answer would be no. The magnetic field seeks to align itself with mu, or it seeks to align mu with itself, but mu and the magnetic field are already aligned here. So I think what we have to say, because I can see it, if I flip on the magnetic field, this is not going to do anything. The potential energy U in this position is a minimum. Again, I'm not saying it's 0, because that is something that we get to choose. We set our reference point. What I can say here, though, is there's no opportunity for it to change. Therefore, it is minimized. Now, I can orient this in another direction. Let me give you some more magnetic field lines. Let me flip the direction of the current here. It's going to be hard to tell that I've done that on a two-dimensional surface, but that's the idea. So now I'm coming down inside the page and up outside the page, opposite of what I was doing here. And I get the magnetic moment, looks like this. Well, what can we say about this? Well, for the same reasons we have here, I think we can say that we can definitely talk about this potential energy is not minimized. There is the opportunity for a change in potential energy here. In other words, if I let this go, it's going to try to flip around. So there is some sort of opportunity for change. So we can't say that it's minimized. However, let me ask you this. Is it maximized? So if I take this and I let it rotate just a little bit, what does that represent? Does that represent an increase in potential energy or a decrease? And hopefully we can see it represents a decrease, right? It's on its way to its 0 energy position, or its minimal position, I should, breaking my own rules. It's on its way to its minimal position. So here is its maximal position, right? If I rotate it this way, it's still, any change represents a decrease in potential energy. So what I can say here is that the potential energy is a maximum. All right. So what have we done with all these mu vectors and b vectors? Well, we did determine the torque which was mu cross B. We would like to be able to use something similar to determine the potential energy. Now, if you remember from Physics 1, or maybe you don't remember, or maybe you never knew, but now it's time to talk about it, the units of torque are Newton meters. Well, what is a Newton times a meter? It's a joule. We don't call this a joule because we're not analyzing it in terms of energy, but the units of torque are actually equivalent to the units of energy. So it looks like if I can multiply mu and b in some way, I can get to the energy of this thing. Well, let me just give you the punchline. We're going to define this as minus mu dot b. So I maintain this mu times b idea where I get units of joules now. I get units of Newton meters here, but I'm going to call that a joule here. So let's talk about the dot product, what it does, and let's talk about the negative sign and why we need that in there. So remember, the dot product reaches a minimum when these two vectors are perpendicular or orthogonal. It reaches a maximum, at least by magnitude, when, all of this is by magnitude, it reaches a maximum by magnitude when these vectors are pointed in the same direction. Really, it reaches a minimum when these are anti-parallel. But in magnitude, it reaches a minimum when these vectors are perpendicular, because that's 90-degree angle, and buried inside here is a cosine function, and the cosine of 90 degrees is 0. So if these two vectors are perpendicular, you get a 0 out of this. If they're parallel, you get just mu b. If they're anti-parallel, that is, one's going this way, the other's going that way, you get a negative mu b. Okay, well, what are we going to do with that in terms of energy? Well, first of all, let me say that this is the purpose of the negative sign. So we've already determined that our potential energy is at a maximum here. We did that just using physical considerations. What do I have in this case? B and mu are anti-parallel. So if I actually perform the cross product here, mu dot b, I get negative mu b. Well, it's obnoxious to have a negative sign sitting in front of a maximum value, so I'm going to put a negative sign in front of my definition so that I get mu dot b in this position. Mu dot b yields negative mu b. And then I put the negative sign here to cancel with that negative sign, which gets me mu b, which is my maximum value. So let me write that. U is equal to mu b. All right, what about the minimum value? Well, because I'm using the dot product here, this is interesting. I get mu b if I do this, if I cover up the negative sign. Mu dot b here gets me mu b. The sine of the angle between them is 0. Cosine of 0 is 1. I just get mu b, but I've already said I need this to be a minimum, so the negative sign takes care of that as well. So if in my maximum position, mu dot b itself is negative, this negative then makes it positive. In the minimum position, mu dot b itself is positive, so the negative sign makes it negative. And so my maximum value is mu b. My minimum value is minus mu b. Now, you might go, well, hang on a second. I thought my minimum value was supposed to be 0. That's what they told me to do in all my conservation of energy problems. And if you're dealing with something like a roller coaster or gravitational potential energy, that's usually the best way to go about it. This one's a little different. It's handy to be able to talk about the energy in terms of the dot product, but because of the geometry of this thing, at a minimum position, if we're going to use the dot product, we get a negative value. And so the convention here is to define the 0 point halfway. Let me get another sheet. We're gonna set our 0 point for potential energy, which we're free to set anywhere, right? By convention, we're gonna set it at this point. So there's my magnetic field. Here's my current loop. Here is my magnetic moment. So at this point, what we can say is that the potential energy, I should tell you the current direction, potential energy is 0 here. Fair enough. That seems kind of strange, but it's okay. Because we know in this system, when the potential energy is 0, it is still going to move. And like, again, that's a little bit different than how we usually did it when working traditional mechanics problems. We set our 0 point at the point where there was no more opportunity for a decrease in potential energy. That's not the case here. There is an opportunity for decrease. This is just so that the dot product works for us, because it's a handy way to configure this. You just have to know that by convention, we're going to let the potential energy be 0 when the coil is in this position, and maximum when the coil is in this position, and minimum when the coil is in that position. Notice when I do that, my total change, if I go from here to here, my total change in potential energy, that is the largest change in potential energy that I have available to this system, is equal to 2 mu b. From mu b to 0, and then from 0 to negative mu b. So my delta u, the total amount of change I have available is this. Now, if I start off in a different position, I'll see a smaller change, but all I've got is from this position to this position in any case. So this is a nice little set of formulas that completely characterize the motion, or at least they along with other mechanical equations. This gets you started characterizing the motion of loops of wire embedded in magnetic fields. The torque on that loop is given by mu cross B, the potential energy negative mu dot B.